Welcome back, ladies and gents. This is Energy Changes Lesson 4, and it's chemical cells and batteries. This is a chemistry only topic, so if you're on the double course doing trilogy, then you do not need to watch this lesson or the next one. Right, so AQA specification, this is what it says that students need to know about cells and batteries. So pause the video now if you want to read that further. Okay, a quick starter. This is what we did last lesson. So if you're unsure about this, you need to go and look at the bond energies lesson. But if you're okay with this, then pause the video, give yourself 5 minutes to try and answer this question. Right, so to answer this question, we need to write out our equation. I mean, it's been given to you there in the question. And we need to look at the bond energy values for all the bonds we have in our reactants and products, and then calculate the total energy change. So for our reactants, we've got 146 for that oxygen-oxygen bond in the middle of the hydrogen peroxide. And then we've got 2 lots of OH bonds either side of that at 464 each, giving us a total energy there, bond energy of 1074. In the products, we've got 2 OH bonds in that H2O molecule, so that's 2 times 464, which gives us 928. And then we've got the oxygen-oxygen double bond at 498, and there's just one of those, so it's 498 again there. So then we consider the moles. So in the equation it tells us we've got 2 moles of our hydrogen peroxide, so we need 2 lots of our 1074. We then, so that's going to give you 2148. We then look at the water where we've got 2 moles, so we times our 928 by 2. And then on the other side we've got 1 lot of our oxygen there, so it's 1 times 498. So our total energy in the products there is 2354. So as we know, we need to minus the products away from the reactants, so 2148 minus 2354 gives you a total energy change of minus 206 kilojoules per mole. So the second part of the question asks you to explain, in terms of bond making and bond breaking, why the reaction is exothermic. So the reaction is exothermic because the energy needed to break the bonds is less than the energy released when the new bonds form. If you got that right, guys, then give yourself a pat on the back, because that's some higher level stuff, so well done. Right, looking at today's lesson properly. So electrical cells and batteries. Electrical cells and batteries rely on the differing reactivity of metals. Okay, so you need to be able to remember the metal reactivity series from topic 4, which is chemical changes. So just pause the video now and have a go at trying to remember that. Good, if you've managed to recall that reactivity series, then you're doing really, really well. So you should have at the top the most reactive potassium, and then at the bottom the least reactive gold, and then the other metals listed in between. So in order to be successful with this topic of electrical cells and batteries, you do need to recall stuff from topic 4. Okay, particularly this reactivity series that we've just done. You need to be able to use that series to predict displacement reactions and construct ionic equations. That's another high level skill there, so if you need to go back and look at that, then I would suggest you do that. And then also recall definitions of oxidation and reduction, and that would be mainly in terms of the movement of electrons. So let's try an ionic equation first. We've got a reaction here between zinc and copper sulfate to give us zinc sulfate and copper. So this is an example of a displacement reaction where a more reactive metal has displaced a less reactive metal from its compound. So the zinc being more reactive than the copper. So if you think you know how to write the ionic equation, have a go, pause the video and do that now. Otherwise, we'll look at that shortly. Okay, so when we're doing our ionic equations, the first thing we need to do is write out in full what ions we have moving around. Okay, in the zinc, it's solid, so there won't be any ions there, and it's an element, so we're not going to have the ions splitting up, and the same for the copper on the right. But our aqueous solutions, we will have ions floating around there, so we need to separate those in our equation. So the zinc stays the same, then we have copper 2 plus aqueous ions, our SO4 2 minus sulfate ion, and then on the right hand side of the products we've got Zn2 plus aqueous, and again the sulfate ion. Okay, you notice that the sulfate ion appears on both sides in the same form, it's SO4 2 minus. Alright, so that's what we call a spectator ion. It's unchanged. Okay, nothing happens to it in the reaction. And we can eliminate that from the reaction. We can take that out. So we take that out and then we drop everything else down into another written out reaction. So you can see the SO4 2 minus has been taken out on either side to give us zinc plus copper 2 plus reacts to give you zinc 2 plus plus copper. Right, so that would be our ionic equation. But what if we had to do half equations? So remember, half equations you will have looked at in terms of what's happening at electrodes during electrolysis. So what we mean here is we want you to be able to show in a half equation how copper 2 plus has become copper and how the zinc has become zinc 2 plus. So if we start with the Cu2 plus, our copper ion, so the copper ion is going to gain electrons, and because it's 2 plus it needs to gain 2 electrons to become a copper atom. And if you remember back to the chemical changes course, the gain of electrons is reduction. So our Cu2 plus ions have been reduced to copper atoms. When we look at the zinc becomes a zinc ion, okay, and it does that by losing electrons. Okay, so we show it in the equation by having zinc goes to Zn2 plus 2 electrons. So the loss of electrons there, okay, is oxidation. So the zinc atoms have been oxidized to Zn2 plus ions, zinc ions. Now it's convention to always add electrons. Okay, some of you might be tempted to say zinc minus 2 electrons. Okay, but it's convention to always add the electrons, which is why they've been added onto the side where the zinc ion is, to show that it's lost those. Okay. Alright, the equation we've just looked at then, that shows how a more reactive metal will donate electrons to a less reactive metal. So in that example, the zinc was giving up electrons to the copper. Right? So those two half equations, we saw how the copper was gaining electrons, whereas the zinc was losing electrons. So the difference in reactivity between two metals can be used to influence the flow of electrons between them. So if we've got a movement of electrons between two metals, a flow of electrons, we know from physics that a flow of electrons is equal to a current. So if we could join two metals together via a wire, okay, and dip them in an electrolyte, which allows the flow of our ions, okay, the electrons will flow through that wire from the most reactive metal to the least reactive metal. And that flow of electrons can be harnessed and used to produce electrical energy. And the current will keep going. It will keep going it will still have movement of electrons from the most reactive to the least reactive until all the reactants have been used up. So here's a diagram of what we were just talking about. This time we've got magnesium and copper in a salt solution, or sometimes it's a dilute acid. And you can see from the diagram the arrows on the wires showing the electron movement. And it's going from magnesium, the more reactive metal, to the copper, the less reactive metal. So all metals have this tendency to give up electrons. Okay, they all want to give up electrons to get that full outer shell of electrons. The more reactive the metal is, the greater the tendency to do that. So where there's two metals both wanting to give up electrons, it'll be the more reactive metal that gives it up to the less reactive metal. And that flow of electrons between the two we use as a current, and that can generate electrical energy, and that's why the lamp is coloured yellow, to show that it's on. Okay, the greater the difference between these two metals, then the higher that voltage will be, the higher the push of that more reactive metal pushing those electrons round to the less reactive metal. So if both of those rods were copper, they're both the same reactivity, so there's no difference there, there's no difference in push, there'd be no flow of electrons, there would be zero voltage. And then if we had a less reactive metal, for example iron, then you still would get a voltage, you still would get a flow of electrons from the iron to the copper, but because the difference in reactivity isn't as much, that voltage will be lower. Right, let's apply that now to this question. We've got an example of an exam question here. There's a cell on the right hand side and then a table with some values. You can notice that electrode A is always copper, and then they change electrode B and they see what the voltage produced is. So give yourself 3 minutes now to have a go at that question. Excellent. Hopefully you've whizzed through that in 3 minutes or less. So the first question here, list the metals in order of reactivity. So you may have done less reactive to most reactive. We're going to do most reactive at the top and least reactive at the bottom. So from the table, the one with the highest voltage, that's going to be our most reactive, because that's the biggest difference in reactivity between the metals, which gives us our highest voltage. So magnesium will be our most reactive there, and then we'll have zinc, okay, and then the next one along would be iron, and then we'd be down to tin, and then finally at the bottom you'd have copper, where there's zero voltage because they're the same reactivity. So you may have done that the other way around, you might have had it in the reverse order, alright, but well done if you got that correct. Then the part at the bottom here, batteries consist of cells. Okay, we know this from physics that a battery is multiple cells. So describe how a 6-volt battery can be made from cells of voltage 1.5 volts. Alright, so hopefully this was relatively straightforward for you. But if we have 4 1.5 volt cells connected in series, that'll give us a 6-volt battery. Right, batteries themselves. So batteries are essentially primary cells, and modern batteries are basically versions of this, and they're still manufactured today. Standard batteries cannot be recharged. Alright, so once those reactants are used up, then there's no further flow of electrons, and therefore there's no further electrical energy being produced. So once the reactants are used up, the reaction stops. This is the same for alkaline batteries. Okay, they follow a similar process. Rechargeable batteries, they have a reaction going on in them which is reversible. So they can actually be hooked up to a power supply that can reverse the reaction that's been going on at the electrodes and then set it up again to be used once more. Okay, but over time, okay, that kind of facility will degrade, and you won't be able to use it forever in that way. Okay, so rechargeable batteries, they will degrade over time. All right, but that reversible reaction, that essentially regenerates the reactants and it can be used again. But most normal batteries, once the reactants are used up, then the flow of electrons stops and there's no more electrical energy being produced. Right, thanks very much for watching that, guys. That's the end of lesson 4 on batteries and cells. The next lesson is on fuel cells, specifically hydrogen fuel cells. Again, this is a chemistry only topic, so if you're doing the trilogy course, then you do not need to watch that video. But hopefully I'll catch up with you next time.